Hey friends, there's something new from our sponsor Text Control. Their new product, DS Server, provides document services out of the box for all platforms and languages. Whether you want to integrate document creation, editing, sharing, or collaboration into your web app, DS Server provides the back-end technology to integrate that professional document processing. For example, using DS Server, you could integrate an MS Word compatible document editor into pure JavaScript, Angular, or an ASP.NET Core application. You can create PDF documents using Web API calls or even request electronic signatures from end users. DS Server is also hosted on-premise in your infrastructure or with your cloud provider, such as Microsoft Azure. And you can test DS Server without downloading anything. Create your first DS Server application in minutes by requesting a trial token on their dedicated website at dsserver.io. That's DSSERVER.io. Hi, this is Scott Hansel, and this is another episode of Hansel Minutes. Today I'm talking with Sam Scott. He is the co-founder and CTO at OSO, and he's completed his PhD in cryptography. How are you, sir?
I'm doing very well, Scott. How are you?
I'm very well and very excited to talk to you. You know, I've been doing a class, kind of a informal class on my YouTube recently called Computer Stuff They Didn't Teach You. And I'm excited to talk to you because I feel like not every software engineer understands the things that they maybe need to understand around cryptography.
Yeah, I think that's right. And to be fair, it's a large topic, cryptography and security in general. So let's see if we can address that.
Well, you are the CTO at a company called OSO, which has a piece of the Secure Pi. Like, this is an authorization service. So you're making sure that people have access to the things that they need to and not access to the things that they shouldn't have.
Yeah, that's exactly right. And, this is all within the larger mission of OSO, is really around making security something that is easy for developers. That's kind of the whole point.
Okay. So when I talk to developers, when I interview them, often I'll use one of my favorite interview questions, which is, you go to your browser, you type, google.com or Bing, and you hit enter, and what happens? And the joke is that, well, from what perspective? Like, do you want to talk about the keyboard? Is this a job for a hardware engineer? Let's talk about how the enter key presses and metal touches metal. Are we going to be a physics person? Let's talk about the electrons or the Bluetooth or the USB. Let's talk about, you type in Google, you hit enter from a security perspective.
Yeah, that's a great one. So first of all, there's a piece which maybe we won't go into too much detail, which is there's a whole DNS piece of this, which is your computer's going to effectively look up where is Google.com, what's the server that it lives at. Mm-hmm. But from there, what's happening. You've established a connection with Google.com, and the first thing that's going to happen is you're going to try and establish a TLS connection with Google, right? So this is effectively a secure channel where you're trying to establish that this is actually Google you're speaking to, that you have some kind of proof that this is Google, right?
Okay. So I type google.com, and assuming that my browser didn't use what's called HSTS, which would have gone looking for a secure connection by default, do I connect over port 80 and then I get quote unquote promoted to a secure or redirected to a secure
Exactly.
port?
There's a few places this might happen, but most web servers these days will automatically redirect any plain text HTTP traffic to the secure port, or say no, you should go to HTTPS. Once you go there, then your browser knows, okay, I'm expecting this to be a secure connection. I'm gonna try and establish that.
Okay. So what is that conversation? Because I know I type google.com, I press enter, and a lock appears. So there must have been a lot of chatter happening to make that lock happen.
Right, exactly. So, and again, this may not necessarily be the case with Google, and depending on the browser, but in general, what's going to happen?
We can use Hanselman.com, whatever makes you happy.
Hanselman.com, that sounds good. So, supposing I haven't visited Hanselman.com before, right? I have no pre-existing relationship with the website. I've never been there. My computer doesn't have any special knowledge about it. So Hanselman.com is going to need to present me with a proof of its identity. So it gives me back what's known as a certificate. And the certificate says, this is Hanselman.com, and you know this because I have a certificate proving it, and the certificate is signed by a certificate authority. So these are, there's a small number of these, and their job is effectively to dish out these certificates to prove that they've verified that this is indeed the owner of handsome.com. And there's
Okay, what does that mean? That you trust handsome.com because you and I have shared trust with an authority?
That's exactly right. Yeah. So, for example, there's one that's been growing massively over the last few years called Let's Encrypt, where they've established a free service for this. So that there is a Let's Encrypt certificate authority, and actually in the past they had their certificate signed by another one. We're going to see this as a recurring theme throughout this entire conversation. This turtles all the way down kind of thing. Trusting who trusts who trusts who. But in this case, keeping things reasonably simple. Suppose you have a certificate from Let's Encrypt. I trust Let's Encrypt. I maybe have a relatively small number of these certificate authorities like hard coded in my browser or my computer that I trust. So when I see the certificate from you and I can check that Let's Encrypt were indeed the one who gave you that certificate, then I'm like, okay, that's good. I trust by association here. Yeah.
Okay, so I show up at the border. I have a passport. We do have to make some assumptions. I'm a human. You're a human. We are familiar with the concept of a passport. We agree that passports are a thing that can at least prove, or at the very least, assert my identity.
Mm-hmm.
So you just said hard coded. So my browser does have to bootstrap itself. It needs to at least know of some main top level root concepts like there are certificates and there's an authority for them, or at least some number of them. Can it update that? Like, can a new certificate authority assert itself and appear in the universe?
Yeah, absolutely. And that'll be the process that browsers will go through when they update, for example. So you maybe get a new Firefox update, and maybe it comes with a new root certificate authority that's been added.
Okay. So we start with that assumption. I, handsome.com, present the certificate to you. How do you know I didn't just fake it or make it up?
Right. So this is where we get into the kind of cryptography piece of it. So all of this, certificate authority certificates is part of what's known as a PKI, a public key infrastructure. And it's all based around this area of cryptography called public key cryptography. And the sort of the public piece is referring to the fact that you can have this kind of part of your cryptographic key, which can be public information, and it kind of provides you with some cryptographic material that you can kind of share out in the world. That allows people to do this this kind of verification operation. It's this like two-sided thing. So if I have so the key pair will be made up of two parts: the public part and the private part. The private part, which would be the piece that, say, Let's Encrypt has, can be used to do a signing operation. So they can sign the information that you give them and say, yes, Let's Encrypt have checked this. I have cryptographically signed it and put it out into the world. The public piece, which would be the piece that is downloaded and stored on your computer and your browser, can verify that signature cryptographically. And this public-private key, this public key cryptography, these are the pieces that are all based around effectively number theory, number theoretical things coming from maths, hard problems that can't be solved and can't be broken, and use some really interesting constructions to solve.
Okay. So I receive a letter from the king, and it's got a cool wax seal on the back. And I flip it over and I look at the envelope and I go, this is a regular envelope. And I see the wax seal and I go, wow, that's elaborate. I don't think I could fake that. I've seen that before. I trust that. I know that that's the king because he made it with his ring or whatever. And I get the public part, which is the chunk of wax with the impression in it, but I can't make it because I don't have the ring. And why do I trust it? Maths.
Yeah. So maybe the public part is maybe the king puts notices up in the town square to say this is what my seal looks like. If you see this on a pushed into a wax seal, then you can trust it. So now the wax seal here is maybe the signature saying that this thing is authentic. You pop open the letter and you look inside and you have the this piece that you now know comes from the king.
Okay. Now, TLS, I've heard that more and more lately. Like, I didn't think about TLS 10 years ago when I started thinking about cryptography. Now I hear about it all the time. And now I hear about versions of TLS. What is TLS and why does it need versions? And how does that relate to SSL?
Yep. So TLS stands for Transport Layer Security. It is effectively the evolution of SSL, which is the secure socket layer. So we switched over from calling it SSL to TLS quite a few years ago now, but they're effectively representing the same core objective, which is around establishing and securing a communications channel between two parties. So there are two parts of TLS. There's the handshake protocol, which is this kind of initial piece you go through where you establish identities and you share cryptographic material. And you kind of do everything you need to kind of get the conversation up and rolling. And then the second part, which is the record layer protocol, which is, once we've established our cryptographic materials, how we actually do this kind of encrypted, authenticated channel to each other.
Okay. And when you say it's the next version, is it a situation where we should just stop saying SSL and just start saying TLS, or is that just an implementation detail?
It's a good question. I feel like it's a potentially more controversial in some circles. It's pretty common, I find, to see people just write it SSL/TLS to kind of all be on the same page which one. But if you're actually using a version which is called SSL, then you shouldn't, because those are very out of date. You should be looking at using TLS 1.2 or 1.3, where 1.3 is the most recent one that was sort of standardized kind of in the last year.
So it sounds like it's a branding thing. Like when I say Kleenex, I don't necessarily mean the Kleenex brand tissue. I just mean tissue generically. So SSL is a thing that we don't use anymore that is deprecated, but everyone knows what you mean when you say it.
Exactly.
Okay. So that doesn't sound too bad.
No.
It's a branding issue, but we know what we mean. But you're right. If you are using the original SSL, if you're using original brand Kleenex, you might want to check out some of our new tissues that are improved.
Exactly.
Okay. So then I've proven that it is in fact Hanselman.com that I'm talking to. Is that trustworthy? Can I trust that? And what's the difference between privacy and trust?
Yeah, so the trust piece of this, everything we just spoke around about the PKI and doing certificates, it's used as a piece in that initial TLS handshake I was just talking about. So, when I'm connecting to Hanselman.com, I get the certificate. That's my piece of the trust. I'm like, because I trust certificate authority to have given you a certificate, and I think probably no one's meddled in that and done something suspicious, I'm going to trust what I get from you. And what I'm going to get from you in the TLS handshake is pieces of cryptographic information that allow us to establish a shared key. And so this happens through a process called Diffie-Hellman, which is another piece of the kind of public key cryptography world. But instead of being about signatures that we just spoke about, it's about establishing a shared secret that only you and I know, but nobody who is intercepting the traffic in between can work out.
Okay, so it isn't necessarily proof that it is me, but it's proof that it is a quiet conversation, that we're really talking just to us.
Exactly. So by the end of the TLS handshake, I'm like, okay, I now know that you and I are the only ones who have this piece of information. We can use this to derive a encryption key and encrypt the traffic between us. So this is now an encrypted channel. It's a secret channel between you and I, and only the person who I'm, only someone who could have gone through that whole PKI trust certificate process would be able to have that key. So whoever that person is, we have privacy between us. Nobody can snoop in on the traffic that's happening.
Why wasn't SSL perfect, and how do we know that TLS 1.3 isn't perfect also? Like, you're saying all of these things are because maths. Do we then discover that it's not the case, or are computers getting faster? Like, why is this not the final word on this topic?
Yeah, sort of all of the above with what you just mentioned. So there is some of this which is, over time we are, evolving our understanding of what it means to have a secure encryption between the two of us. And for example, one of the big changes in TLS 1.3 was around this concept of forward secrecy, which is even if someone was to snoop in on our encrypted connection for now, for example, and then later we're able to get access to some of the cryptographic material that those servers had on hand. So the keys that were used to establish that initial connection. Even then, they won't be able to retroactively decrypt and see our traffic. So this is like something which is like a really strong guarantee that just because someone's listening now doesn't mean they can work out what we spoke about in the past. And this wasn't something that was previously that well understood, and it wasn't something that was like an objective of the earlier versions. But as the primarily the academic community is like understanding these new notions, they can kind of start trying to involve in the things we design. So that's kind of one piece of it.
So in the future, like 10 years, 20 years, 100 years, theoretically, the maths and the underlying stuff in this technology will be maybe versioned and flavored and have a little extra this or that, but are the fundamentals correct?
Yeah, I'd say the fundamentals are very, very strong. And actually, one of the things that made TLS 1.3, the process of it, very unique was that unlike some of the previous versions, the academic community was brought in at a very, very early stage. And this was something I was part of as well, as being in academia at the time, was applying some of the latest and greatest techniques to understanding, is this protocol secure, from everything down to the kind of mathematical proofs of each of the pieces, to things like formal methods, which is like running these kind of exhaustive computational checks on, could an unbounded number of attacker who could listen into an unbounded number of clients find some combination of passing messages to kind of break the security. So there's this very rigorous process that went through 1.3 to avoid some of the mistakes and mishaps that happened in the past. Some of which are cryptographic, involving cryptographic attacks. Some of which are, you're sort of more of a maybe implementation details or just combinations of things that weren't expected.
Mm-hmm. Okay, so I've secured my Hanselman.com connection with you, and maybe you're going to log in. You're going to put in your username, your password. You might do it, two-factor auth or whatever. That occurs over the top or within the tube that is our private conversation that is secured over this encrypted connection. But the way that we're checking passwords and things, does that have anything to do with the certificate that we're talking to?
Yes and no. So not currently. So right now, what happens is I have this secure connection. So I feel pretty confident that I can send my password, over that secure connection, and no one else is going to intercept that and snoop in on it. So I'm going to send my raw password to you, and you're actually going to compare it with something that you stored. Now, you shouldn't be storing my password in plain text, because the problem with that is if someone does get access to that password database, then my password, which I shouldn't have, but maybe have reused in multiple places, is now kind of compromised and exposed to the world. So what you should be doing instead is storing what's called a password hash. And the idea there is you take my password and you basically apply a lot of computation, which can only go in one direction, so that nobody can kind of work it backwards. It's allowing you to compare a password you get from me in the future with the kind of this new hashed version of it.
Okay.
So that's what the current version looks like today.
But it is important, or interesting at least, for an application developer to note that the SSL and the TLS communication, the way that that's implemented, isn't related currently or directly used from the application developer's perspective on how that password hashing is occurred. Those are two different things. For example, you and I make a phone call, our medium, whether we use Signal or WhatsApp or the actual plain old telephone, is different from the language we choose to speak on the call.
Exactly. And in this case, we send over my password, and I'm like, okay, the channel is probably fine to send the password, but I'm in some sense putting a little bit of trust, coming back to that word, in the backend service in the other party to responsibly store and hold on to that password and not just leave it in an open text file, for example.
Okay, so to be able to submit a login form and enter a username and password and do those things, we are assuming a secure channel, because we don't want anyone listening in, and we are assuming that we're not storing just your password in a text file somewhere.
Exactly.
Okay. Have you ever wondered if you can be offering a faster, less buggy application experience for your customers? With Raygun Application Performance Monitoring, you have all the information you need at your fingertips to find and fix errors and performance problems across your tech stack down to the line of code. Raygun makes it easy to monitor the impact of your performance improvements, quickly identify and resolve issues, and see how your code performs in the hands of your customers, saving you time, money, and sanity. I've personally used Raygun on my iOS apps, and when a user hits a crash, those crashes get centralized into one location, they get bucketed automatically. I'll get a call stack and an email with a line number where things were crashing. It felt to me that I got a gift from my customer in the form of a bug report that I could actually solve. Head over to raygun.com and try it out for yourself. That's raygun.com for a free 14-day trial. There's a checkbox when you fill out a form that usually says, remember me. And there's a joke going around the internet right now that maybe that's not even hooked up to anything. And that may be another whole podcast about, is the remember me button actually hooked up? But if they wanted to remember me, what are they remembering? Are they storing that password hash? Or are they just sending a bit that says, yep, that's the same guy again?
Mm-hmm.
How are they remembering me?
Yeah. So first of all, let's think about what we've done so far. So we were, in the initial kind of TLS piece, I was able to get assurance that I was actually speaking to, say Google. But now Google's saying, well, I need to know who you are, so enter your username and password. So we've kind of done this, a little bit of bidirectional checking who each other is. But because this username and password, process is a little bit, painful to have to do every single time, this remember me button could be hooked up to, something like a token that could be given back to me to say, hey, in the future, to come back with this token. I'm going to give you something that means you can skip this whole process and your browser is just going to handle it for you. Take this token, and I trust it because it's coming from myself, or Google rather will trust it because it's coming from themselves, that they can check it and be like, oh, yeah, I saw you before. I know who you are.
So I saw you before and I know who you are. Could I attack, or could I pretend to be you by faking that remember me?
Yeah, so no, because if Google has configured it correctly, then the tokens that they give you, that like piece of information that they give you to hold on to, will be cryptographically protected. And in this sense, this is almost like a conversation between Google and itself. Sam logged in. I want to give Sam this cookie so that he can come back and log in easier. So I'm gonna encrypt a piece of information saying whoever has this is Sam. I'm gonna give it to Sam now. So Sam comes back. He presents this same token. Google says, "Oh yeah, I trust this. This came from myself." So it's symmetric encryption. This isn't necessarily the kind of same public key thing we spoke about before. Mm-hmm. And Google says, I trust this. I can read that this is indeed Sam.
What if I found that cookie on your disk and then I emailed it to myself and I copied it into my browser?
Then I'd be in trouble. So this is kind of a big concept of secure cookies in browsers, and there's so cookies are this general mechanism for browsers to remember information that or to store information they have about a website they're talking to. So these can be used for things as innocuous, as remembering whether you prefer to see a page on light or dark mode, right? But that doesn't necessarily mean to be secure information. I don't mind if you share that with other people. But a secure cookie should say, this should only be used with this website. In particular, don't go and share this secure cookie with some other website, because if that person's malicious, they could then pretend to be me back to Google.
Okay. So then and that's another in the chain of trust that we're talking about here. The chain of that trust is assuming that the browser can store that cookie, and their generalized cookie storage mechanism is a smart one.
Yep.
And that I would not be able to do that as easily as I just described it.
Exactly. And you'll see the server, Google can tell the browser how to treat the cookie. And so you maybe see this, you can go into your browser developer tools and look at cookies, and it might say something like, same site or cookie equals secure, or some piece of information like that, which is saying,
okay,
don't use this outside of this context.
Okay, so a cookie can hold anything. It's a name value pair, and I could say remember me and include things. But they can also store. They could have claims. I could claim that I'm an administrator or that I'm in charge of something. That's where we go from authentication into authorization, right?
Yeah, that's right. So imagine, again, you're Google and you have hundreds and thousands of services. Maybe the login functionality, you don't have to go back to that user service and be like, oh, remind me again, what role does Sam have in the company? Oh, that's right, he's the admin. Okay, maybe you don't have to go back and ask them that each time. You say, well, I'm already asking Sam to pass around this this token to say that he's Sam. Why don't I also include information to say Sam's the admin of the OSA organization? Mm-hmm. I put that in that same piece of information, and now I go and visit some other Google service, and it's just saved itself a bit of work there. It's got that information in there.
Now, when I've written authorization code in the past, I've literally written if user.isAdmin or if user.isEnroll, and then I kind of end up making a bunch of if-thens that describe whether or not a person can or can't do something.
Yeah, no judgment. That is a incredibly common pattern that I think most people out there are applying today. But it's actually it's not the only approach, and there's sort of a growing area for expressing authorization as policies. And so that's actually what we're doing at OSO is we're building an implementation of a policy engine. It's an open source policy engine that allows you to express that kind of authorization logic that typically, as you say, is like if and else and nested things using a declarative language.
Okay, so if I wrote a bunch of procedural language that said, if I'm an admin and admin is a hard-coded string, then I'm allowed to go and delete expense reports or modify history and do all kinds of evil things. That's a very naive and simplified way to do authorization and probably not very secure. You're just saying that what OSO does is declarative.
Yep. Yeah, so it's declarative. It's also logic-based. So it means those kind of heavily branching logic, if it's an admin, do one thing. If they're not an admin, do something else. If they're not an admin, then maybe check some, that is very, can be very concisely represented with, this like logic-based declarative approach where you sort of just typically write down a set of rules, like says, admins can do this, members can do this. And then maybe the branching happens elsewhere. You say, well, if the user's an admin, follow down that path. So that kind of allows you to represent it quite concisely. It also means you kind of get to write more of these sort of like higher order logic over your authorization rules. You can sort of pull out common pieces into reusable logic, and it kind of gives you one place to do all of that stuff. So you write all that code in your policy file. In the case of OSO, you can actually write those rules and that logic over your application data, so you don't need to worry about hooking up OSO to your database somehow. It just kind of all happens in the app.
Oh, that's nice.
Yeah.
That sounds like it maps, like we've been using a lot of analogies to describe my mental model and how I think about security. Oh, it's like this and oh, it's like that. So this is a way to basically almost bring the mental model that one has about how someone's allowed to do something in the system into a nice declarative, clean way to express it in OSO.
Yeah, that's exactly right.
Okay. So we've established our relationship. We've established our connection. We've logged in. We've checked our password with password hashes. We've stored, some token, maybe some claims. So we've decided that I can do some things, and I claim my dominion over some piece of technology. That is cryptographic as well. So when you're checking if I can do something, it's not just because I said it. Mm-hmm. It's because the claim itself is also cryptographically significant.
Right. That's exactly right. So, in this case, it might be the entire token will be encrypted or something and assert various pieces. Often there's, maybe it's a bit of a hybrid approach. So a lot of the time with something like OSO, what we see is that the various checks might be done in real time, hitting the database in the application to say, well, is the user in this particular organization? The sort of benefit of that approach is you can kind of make that real time check. You don't, if the user left the organization but shows up in an old token, then it's
good point.
Yeah, but
they could have left the organization in the middle of the conversation.
Exactly, and this is like a very hard problem to solve, and it's the balance or the trade off here is passing the information in a token. It allows you to kind of cryptographically assert that at some point in time this was true, and it saves you maybe doing some work in the future. But the trade off is you maybe have this period of time where the information might have changed, but you haven't got any way of checking that.
Okay.
Yeah, this is related to as well, like a whole, everything we spoke about pretty much here today also has this idea of revocation, which is if you've put some information out there and you want to revoke it, you want to say this is not true anymore. So revoking a certificate is this certificate is no longer valid. I want to revoke it from the world. This is like a whole extra separate complicated world of like, well, how do you update this? How do you for certificates, for example, there is a central list of all revocations. So you basically need to broadcast to the world, this certificate is no longer valid. Everybody update your lists of revoked certificates on your browser so that you're not going to trust this expired key. It's and that's to combat this downside of having these things that can persist over time.
So I've got this end-to-end conversation. We've heard that end-to-end encryption, and everyone's talking about. Before we used to say this is encrypted, and we have a little image on our website, like Hansman.com, and have a picture of a lock, and they go, "We're encrypted by and you should feel good about that." But now we're seeing more and more websites, companies, WhatsApp saying this is end-to-end encryption. What does that mean to have end-to-end encryption?
Yeah, well, it depends on what the ends are. So you might say end-to-end, meaning from my browser to the website. That's those are the two ends that are encrypted. If I'm having a conversation with with Google, maybe it's encrypted to the Google servers. In the case of WhatsApp or a messaging, client in general, what you probably want or what you probably mean from end to end is between you and me, even though this is passing through Facebook servers, the encryption is happening between you and I so that they can't snoop in on the traffic that's passing. Even though it's passing through their servers, they're not seeing any of that.
Okay, but when you say end-to-end, if you call Hanselman.com, you're encrypted from your endpoint, your browser, to my endpoint, which actually isn't a web server just coincidentally in the case of Hanselman.com, it's a what's called an Azure front door or an edge server in the case of like Cloudflare, but you don't know if it's encrypted from Azure front door to my actual web server.
Exactly. So, most applications, most websites aren't just a single homogeneous system unless they're running on a single computer. There's going to be various different hops along the way. So, exactly in the case where you're using a CDN like Cloudflare, for example, or kind of one of these edge services you're talking about, you might have encryption happening from your browser to that server. They might do some decryption there, and then maybe they'll re-encrypt it so that it to go from that edge service to the next hop and so on and so on.
Is that important for me to know, though? Like, who should know that?
Yeah, so
because everyone gets the same lock.
Mm-hmm. Yeah, unfortunately, there's not really a good way as a user to really know what's happening. Your piece in this equation kind of ends once it gets terminated at whatever that first hop is. You get your assertion, cool, this is encrypted, and I can check the certificate, and it says it's a Cloudflare certificate, so presumably they're doing something with it. And then from then, it enters the kind of opaque land of the web server, the web application, and it's a kind of coming back to it's really about trust again. You need to trust that the company, the organization are doing the responsible things with the data. So we spoke about passwords earlier. You give them your password and you hope that they do the appropriate thing with it. It's true for any data you send them or you store with them. You kind of got to hope that they store in your credit card details, encrypted in a database so that someone manages to compromise that piece of the database, they don't get all your data. And if you think about the various data breaches that happen over the past years, a lot of them are they're not talking about data breaches of like TLS or the conversation you have with the website. They're talking about a very specific piece of that entire infrastructure that has been compromised, which hasn't got appropriate data privacy controls, doesn't have the appropriate encryption. So really, there's a huge amount going on under the surface that, as a user, you don't really hear about unless it goes wrong.
Yeah, that is kind of a bummer. From a user interface perspective, the lock, I think my non-technical parent thinks it means a lot, like that this is a trustworthy website and this is a good place and I could put my credit card in here. And it really just means we're talking over a secure line.
Exactly. And that's where, things like, the EU has this data protection thing, GDPR, that kind of entered the phrase to try and address this type of thing, is to go and hold those companies accountable to managing users' data in an appropriate way, because that's kind of where this comes to. It ends up being in some ways a legal thing. The cryptography is sort of, I'm sure there are cryptographic approaches that would solve this problem, but it's more of a legal problem right now to make sure that we go around and hold, make sure the companies are doing the appropriate things, or it's something that we can kind of all do as as developers, as engineers, is make sure that we've done the appropriate controls in our application.
Very cool. I feel like this has been a really good overview of what the average techie or average programmer should know about what happens when you type google.com and hit enter and you get a little lock there.
This was a lot of fun.
Yeah, I really appreciate you hanging out with me today.
Likewise.
Yeah. We have been talking with Sam Scott. He's a co-founder and CTO at OSO. He completed his PhD in cryptography from Royal Holloway University at the University of London. And you can find him all over the internet, and you can check out OSO at osohq.com. This has been another episode of Hansel Minutes, and we'll see you again next week.